given by Dr. He comes from academia since. So the title is Introduction to Symplectic Topology. Let's welcome Dr. Wu.
Thank you, organizer. So I'm very happy to be invited to give a talk here in Tsinghua Dashi. So this talk is going to be a very comprehensive, and I hope it's understandable for college students, for undergraduate students. So it will be about the level of I will just assume you know calculus and some topology, like what you know what is open set, what is closed set, such as this. So my talk will briefly split into two parts. The first is I will give a brief introduction to what is symplectic geometry or topology. And the second part would be an emphasis to some examples of symplectic embedding. So you all know what is Rn, right? It's a real number. It's an n-dimensional real Euclidean space, and we think of this as a position coordinate. So let's say I give it a symbol Q, and we want to assign a counterpart. So it's actually a vector, but I will just abbreviate them by Q and P, and they are from another n-dimensional Euclidean space, and I will say those are coordinates of a momentum of a single particle. Of a single particle moving in Rn. Okay? So the classical mechanics tells us what is the motion of this single particle is controlled by Newton's second law, which is this is kind of very easy. So Q, the position, then T is the time. So the position of this particle Q at time T is a curve. It's a curve in Rn. It's a curve. Rn. And the second piece of information will be, say, U. U is a function from Rn to R. Let's say E. Potential. So the Newton second order law is written as Q, and this is the second derivative with respect to the time t equal to negative partial V partial Q. So if you know how to solve this equation, you know what's the exact motion, what's the position at time t for this. So I'm not going to solve this. I'm just going to give an alternative formalism. It's called Hamiltonian formalism. So think about this. Think about this. So now here we don't see any momentum. We don't see speed, and it's a second order It's a second order equation. And we want to turn it into a first order differential equation. But we have to pay, what we have to pay for is we may have double the number of equations. So this is what we did here. So here, by introducing P, you simply think this is Q, the first derivative of Q. Okay? And you said, let's say, okay, I'm going to use H. Okay, I'll use H. P is a function of p squared over 2 plus qt. Then the equation becomes this. Becomes first you take q. Okay. Let's do this. And p dot is negative partial h partial q. And it's a first order equation. So, but we want to consider a more geometric, in a more geometric way, that such flow, say you assume you know how to solve this equation, and that should give you a flow, not only on Rn, but on Rn times Rn. So that gives you, so this equation gives you a flow. Rn times Rn. Say fix a point. So what is the flow? It's given time t. We don't actually need this, but this is just like negative t. Sorry. The diffeomorphism. To n. So say q p into qt. Q of p, p of t. Here we typically think this is q0. We can get the initial position and momentum, or the initial configuration. So for example, say h equals to this. Then the equation gives you this p and p. So it's very easy to see that the motion of this, the flow of this equation is actually, let's say, this is Q, this is P. So the motion of this is just a circle. It's just a loop. So you start at different initial configuration. You get a full loop. Every orbit turns out to be periodic. And another example, h equals to cosine q. So I'm not going to solve this, but I'm going to draw a picture. So it should look like this. So if you go, so it's actually a combination of periodic orbits and not periodic orbits. If you start from here, you just go all the way. If you start from here, you just go all the way to the right, and maybe to the left. Okay. And if you start inside inside some certain region, just go around. And you see that it can be, the behavior can be very different, especially if you notice that cosine q can be approximately by a constant, so cosine. So if you want, you can just add one to value, but it doesn't matter which constant you pick, to add any constant. So you see, if we only consider the first two terms, it becomes a total periodic behavior. So it evolves periodically. But if you have some kind of different functions, so it's interesting phenomenon because this is a periodic function, but turns out you have non-periodic opens. So such flow, let's say phi. Such flow form a group. So for any function, so this index is for the time. Say a smooth function, we assign t. And B1, such B1 forms a group. A group. And it's a Hamiltonian differential group. Of the group of the differential. So this is the one of the main subjects that we studied in symplectic geometry and topology. So the natural question is, what do PEM preserve? So what do PEM, because we know this one preserve differential structure, and there are many groups. For example, isometry. If you fix a Riemannian geometry, this is like another subject, and you know what they fix. For example, they fix curvature, they fix the Riemannian structure. But what do they? You have a lot of things preserved here. But for example, what do we preserve here? And a classical Riemann theorem says such can preserve the volume form. So what is the volume form here? The volume form is, so Rn is dq1, dq2, dq1, this is the volume form. For example, this one, the rotation. Of course, apparently it preserves this volume area preserving, because here, for example, we have 2 dimensions. And this one is also area preserving, but it's not very easy to see. So it's like if you start from a small area here, and then you rotate about this point. But if you start something here, when involved with something here, when involved, it will be stretched. It will be stretched. trace to. And still area preserved. So the first thing that is preserved is volume preserving, but the modern perspective preserve more than volume form. It preserve such feet preserves this. So it's a two form. When n equals to 2, this is just the area form, the volume form. But it actually preserves more because the volume form turns out to be. So if you preserve volume form, doesn't mean that it preserves omega. If you preserve omega, then you preserve the volume. So now I'm going to give the formal definition of what is the symplectic manifold. So definition of symplectic manifold. It's a manifold. It's a differentiable manifold. A two form. Omega, so slash. You have two requirements. The first is omega has to be non-degenerate. Means that it actually measures some non-zero area. It doesn't degenerate. It just means that when omega restricts any small piece of rounding, it doesn't vanish. So for example, any now equal to 0, 1, 4. And the second thing is omega is closed, which means it's equal to 0, or you may think that equivalent definition is that it integrates to 0 for any closed surface. So I'm not going to explain why this definition are relevant. It's if you're interested, I can explain to you after the talk. But the thing is, it's not that abstract because there is the Darboux theorem. Any symplectic manifold looks locally R2n looks locally like this. So it's so it means that we don't have true local structure. It's not like Riemannian geometry. In Riemannian geometry, we ask what's the curvature at certain points, and you may have different curvature at different points. But here, if you fix the symplectic form, the concept Darboux theorem just tells you that at each point they all look the same. They all look the same. So here the symplectic topology and geometry only cares about global problem, not local problem. And
if I can ask a question, so what's the interpretation in physics that phi preserves volume form or the omega?
It relates to for example ergodicity. So if it preserves volume form, you expect the related dynamic system have some ergodic behavior. I mean, the Hofer theorem is is more related to dynamic systems. So but simplicity is it's actually more than preserving volume. It's preserving a two-point volume.
I mean, does it correspond to anything in physics or in mechanics?
You mean volume preserving or?
Yeah, or preserving omega.
Oh, preserving omega is every, so the flow always preserve omega.
Yeah.
Yeah.
My question is, I mean, to a physicist, what does it mean?
So it just means the evolution of your phase space. The evolution of your phase space. So because in fiction we care more about give you a point and what's the motion. But here this is the global version. We discuss for each point a global flow that flows every point. So yeah. So if time permits, I will try to explain what's more related to physics. Like what's the analog structure in symplectic topology that relates to quantum mechanics, for example. Yeah, but here we will have to specify a little bit that, let's say, be the subgroup. Of multi-segment that preserve omega. So randomly you got the following inclusion of subgroup. So here, if you are interested, I haven't defined what is hand and Hamiltonian differential for general hand, but you can think of what is hand. Hand is the flow. Hand is such that by T is the flow of a vector field xt, and this xt satisfying such equation. This is x h for some h. So this is just the equation. This is just exactly the same equation, but more abstract. So let me try to raise two phenomena that one for each. To reveal the difference symplectic topology from ordinary differential geometry or topology. So the first thing is Arnold conjecture. It's a weak Arnold, to be specific, it's a weak version of Arnold's conjecture. If you are interested in what's a strong version, I can tell you later. So this is about the prediction of the fixed points, the number of fixed points of such T. So the theorem is when M is the condition is when n is closed. B is a Hamiltonian diffeomorphism, namely it's generated by such evolution equation. Then the number of fixed points. Say assume that B only has non-degenerate fixed points. So it gives the lower bounds of the number of these points. So you may want to compare this with a B field. So say psi is a diffeomorphism. The Lefschetz point theorem makes a prediction that it's bounded by which is the alternating sum of this. So this one is actually is bigger than this. Right? So it makes more. It's like when we focus on Hamiltonian diffeomorphism, we do get more fixed points, more than expected. So the second phenomenon is the zero rigidity. So it's called Heisenberg rigidity. So what does it mean? It's a phenomenon about symplectic development. So the theorem says that this one is zero close in So this is a very remarkable phenomenon because let's say we have a sequence. Let's say we have a sequence of P1, P2, okay. A sequence. If we have let's say C1 approximation to a diffeomorphism by symplectic homomorphism, and because all symplectic homomorphisms preserve omega, and it's only about differentiability. So if you have a sequence that approximates to phi in all say first order derivatives, then you expect that this one is actually light in the simp. Because if all of them preserve omega, then the limit should preserve omega. But theory rigidity tell you more about this. So say you have no information about first order derivative. You only know that the norm, say maximum norm or the uniform norm approach to phi without knowing what happened to derivatives, to their derivatives. Then the rigidity theorem tells you that if you know that the limit is a diffeomorphism, then it should be a simply diffeomorphism. So it's a very unusual phenomenon. It's very difficult to imagine when you see your first time to see this. Okay, so I think I'm going to the second part. So the second part actually needs no understanding about geometry or symplectic form, nothing at all. It's just some elementary embedding of open domains. So I am going to keep this. I'm going to keep this. Okay. So now you know that. So the classical theorem tells you that for all Hamiltonian remote it preserves actually both. It preserves the volume form. But how can you tell? How can you tell about what if it preserves volume form, but it doesn't preserve the symplectic form? So this is the celebrated remote splitting theorem. So before doing this, let me try to give a bunch of definition of domain. Let's say A is a number. A is the open distance of radius square root A over pi is a two-dimensional open disk, and the topology is P A1 to AN is just the product of all such things. Cube the two-dimensional cube is an open domain in R2 it's just P and you control the same radius, and I'm going to define what is cylinder. So a cylinder, say V QNA is defined to be A in the first argument, but for the rest, times 2 and minus 2. So, or you may think of this as B, A, infinity, or infinity to the end. Okay? And what is an open ellipsoid? Let's say E, A1, it has n radius is the point such that pi square pi over a I'm going to use J. It's just the ellipsoid. I mean, for n equals to 1, it's just the interior of an ellipse of an ellipse. So with just this kind of thing, suppose the A of radius. I shouldn't say it's the radius A because it's more like the radius of square root of A over pi. And we make these conventions because we care more about the square of the length, okay, not length. And we try to catch all pi, all this kind of pi, because when you are evaluating the area, there's always a pi. So we try to catch this pi, absorbing in the definition. That's why we make this weird convention. So this is just the ellipsoid with all radius set to A. Okay. So I'm going to tell you a very interesting phenomenon. It's called the celebrated Romov's non-splitting theorem. Okay, so if there exists a symplectic embedding, what is symplectic embedding? It's let's say a symplectic embedding between okay, of B, let's say BA, okay, into, okay, I was just, okay, let's say this, it doesn't matter, 1 into B, A, so this is a ball, okay, and this is the cylinder. This is not the precise graph because the graph we can visualize it in 3 dimensions, but it's a purely even dimensional system. So the theorem is so it's an open symplectic manifold inherited by the symplectic structure of R2n. Okay, so let's just fix this symplectic structure of R2n. If you can embed, you can squeeze this ball into a cylinder by symplectic morphic map. Then, yeah, so there is a bound. Okay, or so only. So you cannot squeeze. You can say this is 0.8. You can say you cannot squeeze a ball of size 1 into a cylinder of size 0.8 because for volume preserving map, this is easy. You can just squeeze your ball as thin as possible for decomposition. But for symplectic homomorphism, this is not allowed. This is not allowed. So this is interesting because it shows that the symplectic diffeomorphism is a map far more than volume preserving. Because this is a domain of finite volume. This is a domain of infinite volume. And now he tells us that you cannot squeeze a finite volume thing into an infinite volume thing, and the proof is very difficult. So it is like the first obstruction and I would say the first obstruction other than volume. So so I will try to before we go through other embedding problems, I can just make a quick sketch of the proof, and it's also an advertisement of a technique called microlocal approach. And so previously, Gromov used a very difficult theory. He developed a full theory of so-called J-holomorphic curves in order to solve this problem. And later, people found we can use J-holomorphic curve to do algebraic geometry and more symplectic topology. But here, I'm going to try to make this more conceptually. I can't say conceptually, but more close to classical approach. So, Gromov theorem revisited microlocal approach to give you a feeling like how can we prove that the size matter. So it's okay. So the first step, say there is such map C, okay? Then it can assume there is the I'm going to do in a more general case. So symplectically into E R2 R. So it's an ellipsoid, it's a ball. And for R1 greater than equal to R2, strictly greater theorem. If there exists such symplectic map. So it's like we have the size of R1, and here between the cylinder and the ball, we squeeze another ellipsoid outside R2, but you can stretch to R. Essentially, our root height, to be honest, square root of our root height. So you can stretch them as long as possible for those capital R. But we do interpret that R2 is less than R1. So say we have such a map. Then we can extend. The first step is extend C to let's say to a. So it's a technical part. Compactly supported Hamiltonian C. And so in this case we can assume that supports C. So what is the support? The support is the closure of the point where B doesn't act as identity. So the support means that the point where this B does move something. So we can assume that this one is contained because everything is bounded compact, contained in ER by making a larger number. Okay. So, which means that we have a sequence of inclusion. So B1 includes into E, R2, R, to R. Okay. And the technical part is for such inclusion diagram, we can define a sequence or a diagram of invariants for all open domain. Greater than 0, U is a complex, a chain complex. So this one is the technical part, but it's an invariant, and we are going to apply this invariant to such a sequence of embedding. So after applying this, this one should be B close side. So B R1 because it's an invariant. So invariant is, by definition is it doesn't matter whether applying simply it's a multi-set. Okay. So let's say we have a map because we have the embedding map, and we have something with relevant to the size. E, R2, bigger R, and we also have this a commute diagram. Let's say this is my J, this is J1, this is J2, which means that J should equal to J1, J1 composed with J2. And step 3, choose an appropriate T such that R2 less than T less than R1 because R1 is greater than R2. We can insert a T here, And we also want, because this T also satisfies this. So T less than R. Okay. So the first condition gives us ST to be R1 equals to, if you know homological algebra, let's say 0 to 3, and C with E is 0 at 0 to 3, 0 and V at the second to 3. And C, R, they're just the same at the 0 to 3. So, step 4. Step 4. So step 4, because we have a shifting of degree, say by 2, so there is no match between these two guys, which means that this one should be 0, which means that you compose with a 0 match, you get a 0. Then you got a 0 between this and this, and you got 0 between this and this. And this is actually a contradiction, because all such, by our construction, all such maps. So if that's 0, then cone or kernel J is of rank 2. Rank 2, then, which is a contradiction, because by our construction, every such, we assign to every such thing a complex of rank. I'm sorry, I should have say in this book, rank, let's say equals 1. So it's like the homology. Okay. So this is a quantitative way to realize the Gromov transmission theorem. So I'm going to, okay, for this part, I'm not going to explain how to assign such invariant, but there do exist such invariant. And if you are interested in topological data analysis, those things are persistent modules. With respect to the index T, you can choose any T, any non-zero T, and when T is getting bigger and bigger, you can see how your invariant persistent module involved with T, and to choose appropriate T will give you some topological insight. So I'm going to give you a bunch of interesting phenomena. This is the final structure of the embedding problem, and so far we only know such final structure in dimension 4.
Why is it called a micro-local?
Why is it called micro-local? Because why it's called micro is because we try to, this one can be realized by T star Rn. So we can use functions. In my version, it's actually sheaves on Rn and taking their micro-local supports, micro-local singular supports. It turns out to be a subset in T star Rn. For example, in D-module theory, if you know D-module theory, it gives you a characteristic. It's just for zero that gives you a characteristic, right? And turns out you can use those. You can do things that work. You can try to investigate those micro supports or characteristic varieties to know what happens topologically. For example, in classical function theory for, say, for an open interval, we can construct a function like this, supported only on this interval, and we can use in real analysis. This is like the fundamental building block of everything, or this has to. Okay, but for microlocally, I mean everything lies in D star. There's a D star R1, and so you are not only focusing on an open interval. You can focus on a let's say a coisotopic subset. Let's say this one, or maybe okay, this one, and you can ask if this is going to be your support in R2, and find a function such that it has a micro support on this guy. Yeah. So this theory leads to define some variables. But this is the technical part. So okay. So what I'm going to do is try to introduce several. I'm not going to explain why it happens, but I'm going to tell you what is happening. So there are several amazing things happen in, let's say, in 4-dimension form. Okay, so let's say so E stands for initial, B stands for false. Go to in A such that E1A and this simply back into B. Okay. And since this one has volume, right? And this one has so to have a symplectic embedding, the first thing is volume constraints. So this one is supposed to so the first constraint, volume constraint, tells you that a square. So sorry, the A is a function greater than or equal to square root of A. So when you try to plot all possible, let's say start from 1, all possible value when you vary A, interesting thing happens. So it's not naturally this, but it turns out it has very rich combinatorial detail. So let me divide the interval into 3 parts. Say 1 to top 4, and top 4 to this one 8 plus 1 over 63, and the rest. Okay. So here tau goes to the golden ratio. Yes, so this happens to be something related to the golden ratio. So what happens is this. Dig, say G0 is equal to 1, G1 is equal to, G2 is equal to, say, 2, G3 is equal to 5, G4 equals to 13, etc. So you just want the Fibonacci sequence 1, 1, 2, 3, 5, 8, 13, 34, and you pick this, and so on. You just pick those you just pick those alternates. then what happened is that that an is 1 over Gn squared. So when n goes to infinity, it approaches to tau to 4. And Bn equals to Gn plus 2 over Gn. And you can see that it also approaches to 4. And what happened is that here we have this one, 2. So what happened is that when this C so the law is Cx is equal to x over it's just a linear function when the interval a and bn and Cx is equal to the constant plus 1 and to the next n. So a and bn and bn plus 1 those constant parts, those constants there, and it approached to exactly approach to this point. And between these 2 points, it's almost this function, almost Ca equals to square root of a, almost, without the finite exception of interval. And after this point, it just completely your lower bound. So the only obstruction happens in the interval 1 and 8 plus something. This is 6.8 something. Okay? This is what happens. And you may wonder, do we have the golden ratio? Do we have a similar phenomenon for Hilbert ratio? And the answer is yes. So yeah. So this one is discovered by many people, and I think Dusan myself contribute most. So second example, C. Now between episode and 4, now we're going to consider E and C. So what is E? Oh, it's E and C. If we try to squeeze the ellipsoid into Q, okay, so then, okay, so now there it is 1/8 into C, C4, 4-dimensional phenomenon, and since this one has a volume, so the volume constraint gives you this one. Oh, I just 1/8, and this one has a volume. Let's say a squared. Okay, 8. Yeah, it's great. And so the volume constraint gives you an estimate. See, A is greater than or equal to A over 2. So what happened exactly is the same. 1, 2. I'm going to tell you what is sigma. So sigma is the Hilbert ratio. Not the Hilbert. So So what happened is very similar to Fibonacci sequence, but now you have to use some sequence approach. This is a pale numbers. So let's say P0 equals to 0, P1 equals to 1, Pn equals to 2, Pn plus minus 1 plus Pn. Yeah, okay. This is pale equation, 2 and 1. If you say 1 and 1, that goes to Fibonacci sequence. 2 and 1 is a pale equation. And let's say H, it's just an auxiliary 1. 1 when we start from 1 and H1 equals to 1 and Hn does the same rule. Hn minus 1 plus Hn minus 2, okay? And you just consider E1 over H0, H2 over 2E1, and P3 over H2, and H4 over 2, that's H4 over P3, periodic 4. And that goes to this one. And that's going to be this. And another sequence is very similar. P1 over H0, H2 over 2P1, and P3 over H2, H4 over 3, H4 over, oh I'm sorry, 2P1 squared. Yeah. So this is the auxiliary one. The auxiliary P1 squared. This is P3 over P1, periodic 4, and it goes to the label already. And the approach to the yes. This one. This is so the graph looks like this. Just stop here. Graph here, like this. Exactly approach to the limit point. And between these two is a transitional curve. Most of the curve is just this one, the lower bound, with finite exception. And after this point, it's just exactly your lower bound. Continuous have these finite exceptions? Okay, so it should be continuous. So I mean, yeah, I mean, wait. Oh no. This one is okay. This one is continuous. Yeah, in principle you cannot. Yeah, sorry. So it has some like I shouldn't call it like jumping. So it's what happens here is I cannot describe here, but because it relates to the arithmetic expression of numbers here. So but in the first example you said that this function is mostly square root of a, except that the finite. This function is this one, except at finite interval. Yeah, but so from that on those finite intervals, it's piecewise linear. Different to that. Yeah, it will have to take a different value. It will have to take say from left and right. So we have to say like say from so almost listed, but we have finite exception, and those exception is as far as I remember is like is piecewise linear, and others are just this. Maybe I should check if yeah,
So
yeah, maybe something like this.
So it's not exactly square root.
Yeah, yeah. So yeah, for this part it's not exactly. Yeah, but after this point, it's on the same happens here. Yeah. So I use this all of the time. So I think I should stop here.
Do you know what happens if instead of symplectic embedding, you consider holomorphic embedding?
Holomorphic embedding?
Yes.
Oh, I have no idea, but
what about the Gromov non-squeezing for holomorphic embedding?
for holomorphic embedding, what is Gromov?
You squeeze a ball in a cylinder, so if I want a holomorphic embedding, so what will be the lower bound for the capital A?
I don't know because in dimension, yeah, because in dimension 2. Wait, no. No, I think they are just different problems, very different problems. Yeah. So for holomorphic embedding, I'm not sure because we don't even have a good definition for holomorphic, say holomorphic on the boundary. I mean, in general, this goes to Cauchy-Riemann geometry. But holomorphic
open domain, right? You consider open domain, or your domain are open, so there's no boundary.
So the reason we consider open is for just a convenience. It's not necessary to consider open domain. You can consider closed domain. There's no difference between open and closed.
Yeah, but I mean for open domain, then you can consider holomorphic map.
For open domain,
there will be no trouble on the boundary.
Yeah, if you consider open domain, I don't know, because you want them to be holomorphic or biholomorphic.
No, just embedding.
Just embedding?
Yeah.
I don't know.
So what happens geometrically at these points?
So what happens geometrically at this point? So it's related to say you have a rational number. So you have a rational number, and the thing is this only have in dimension 4. So in dimension 4, you have a map, a moment map. So it's E2 to R2. So E1, E2 to, let's say, pi, we can just E1 squared, E2 squared. So, for example, for a ball, it gives you a triangle here. So, what happens here is about how you can decompose these triangles. How you can decompose those triangles. Say ellipsoid gives you a triangle. How you can decompose this triangle. How you can decompose this triangle into. So it's very indirect. First, they have to relate a problem of embedding one ellipsoid into something else. Convert the problem to a symplectic packing problem. And by solving this symplectic packing problem, they know that. And this is actually sharp. The estimate is actually sharp here. Because they use J holomorphic curve.
But E1A is just one piece. Why do you decompose this triangle?
Okay, so why do we decompose this triangle? Yeah, since I'm not actually the one doing this, so yeah, I Yeah, I don't know, but the main step is to solve another problem. Yeah. But I think this only happens in dimension 4. So after doing this, the technique cannot be applied to other places. Yeah. So let's speak up.